Okay, everyone, sorry, running a couple minutes late here. Let's get started. So we've got lab 3 was due, or I extended lab 3. Any major issues with lab 3? Yes?
In my binary to decimal converter, I have like this multiplying by 0, 1 in 32 format, but when I have a number in binary, in decimal, I have each digit less by 1. Is it the precision? Do you saw such issue somewhere? Because I really
yeah, I think I had that happen when I was, so when you have the point 1.
Yeah, let's say I have 3, 4, 5 as a binary. I convert it and get 2, 3, 4, like one.
Yeah, I think I had that happen once when I rounded down the 2 to the, when you have the point 1, it's 2 to the 32nd power divided by 10. You have to round it up, not down, because it turns out it'll give you a fractional number, right? I think that might have been.
We had a similar issue, and it was the fixed point number when we used it. Charles posted something about it.
Charles posted about it too. It's the same thing I'm referring to though. If you have 2 to the 32nd power, okay, it's 4,294,967,000, or 294,967,296. If you divide by 10, you get the 0.6 here, right? So you want to round up to, you want to divide by 10, and then you want to add, you want to add 0.4, yeah. So I think if you use this number, it should fix that problem.
The thing that I just divided in program calculator, and it doesn't give you fractional, it just give you hex display. So yeah.
Yeah. As a matter of fact, if you look at it in hex, let's see if I copy. If we go to programmer, yeah. If you look at it in hex, it's 1999999A.
And I get 9.
Yeah, I think, okay, so if you replace that least significant digit with an A, it should fix it. Okay, so
I also thought to fix that issue, maybe just give more numbers to the fractional part and having, let's say, not 64, 32, and then let's say 60 and 36 for the fractional. So increasing the fractional, increasing number of digits for the fractional part can give you better precision. So I should make this helpful.
yes, yeah, you can do that too. So I think at a minimum, you need to have. So if you bring in the digits from the hex display, the switches. There's 18 switches. So that would. You might say, okay, I've got 18 switches, I've got 32 bits, so I'll use the other, 32 minus 18, 14. 14, I could use 14 fractional bits, right? But you can actually use more than that, because you can use more than that in your guess. Right, so you have like in the binary search algorithm, you have a guess at the answer, right? And I think in my algorithm, I suggested that you start out with the halfway point. So you know that the answer is going to be between 0 and 512, right? So your guess could be 250. You could start your guess at 256, but you know that the value, the answer, the square root, is going to be between 0 and basically 511.99999, right? So you really only need nine non-fractional bits in your guess, right? And so you could use 23 bits, fractional bits. But when you think about the display, though, when you display the answer, your precision, the unit in the last place is 10 to the negative 5th, power. So your resolution in the hex displays is 1/100,000th, right? Which is going to be 1 over 2 to the 17th power, right? So you only need 17 fractional bits in order to get the max resolution for the hex displays. But 17 is still more than 14, which is what you might have been using, right? So anyway, my point is you can have different numbers of fractional bits for different variables, right? But in terms of your guess, which is the value of the value of x, I think, where, because it's x squared minus s equals 0, or x squared equals s, where s is the switch input and x is the answer, right? The output. You can have, you can decide that. Does that make sense? Okay.
Yeah, so you can pick whatever you want. Just sometimes you don't need too much fractional bits because it still displays on the hex display.
Right. Okay. Now that being said, I don't remember the exact wording of the grading rubric. I might have to go back and look at that. I don't know if you have to be within 1/100,000th of the answer for the grading route. I don't know if there's a grading criteria for that or not. I have to go back and double check.
I think I didn't saw it.
Okay, if it's not part of the rubric, then the precision won't matter as much. I don't remember how we had that worded though. Actually, I think I have it open right now. I probably could. Let's see, lab 3. It's right here. So, rubric. Oh, it's very vague. Yeah, it's pretty vague. Demonstration of bin-to-deck program operating successfully. I mean, what does successfully mean?
Converts.
I mean, if it's successfully, I guess you could interpret that as being, it needs to have a correct output. I think, though, if you're within a reasonable accuracy, it's okay. Oh. Bin-to-deck program deployed on the DE2-115 board, demonstration of your testing suite, and explanation of your testing methodology. So there's more of an emphasis in this rubric on the testing methodology and how you tested it, more than just the...
I think there are eight hex displays and 18 switches, but the maximum value you can get for 18 switches, like FFF on the switches, is less than 8 decimal digits. So you still use of the part of the hex,
right.
Even then also. Right.
And I was just talking about the square root, actually, not... I got ahead of myself. Sorry, I didn't mean to confuse you guys. Yeah, I was talking about the. That's why I'm confused. Sorry, sorry. I was ahead of myself. I'm already thinking about the next lab. The next lab is the square root program. This lab is just bin-to-deck, right? So you just have to get. So that's a good point. So if you round up the 0.10, right, then you should be. I think your answer should be exactly correct, right? You guys, has anyone had an issue where you had rounding error that caused you to get an incorrect bin-to-deck? Okay, yeah. Sorry, I think if you round up the 0.1, you're fine for the bin-to-deck. For the square root, there's a different set of considerations for accuracy.
So follow-up 4, we implement branches and square root with lab 4.
Yes, that's lab 4. Yeah, now let me talk about that now. So we've got lab 4 is posted. It'll be due on the 28th, which is about 3 weeks, right? The problem, though, is that Philip and Charles, the 2 TAs, are out of town for 2 weeks. They're at a conference, the supercomputing conference. I'll be there next week, but I'm not there this week. So I'm going to cover the labs this week on Wednesday and Thursday. And then the week after that, the labs will be canceled because I'll be at the conference. And then the week after that is Thanksgiving week, right? So the problem is you have 3 weeks to get the lab done, but we have interruptions in the labs. So if you need help outside of class this week or in the latter part of next week, send me an email and we can make arrangements to meet. Okay? Yes?
Can you make demos for you?
I would rather you did the demos either for the TAs or record the demos as Charles described on the Dropbox, just for consistency purposes for the grades. Because if we, I don't want to, I may be a more harsh or more lenient grader than them. Okay, and then, yeah, so see the message on Moodle about recording a demo of your Lab 3. And yeah, like I said, I'll be available for office hours, and we will have a quiz this week. Yes?
Where should we submit that demo?
Sorry?
Where should we submit that demo? Like once we video recording it?
Did he have a?
He said he'll make another assignment link.
Oh yeah, he said he'll put a thing on a submission box for that. Yes. Yes.
Do we have lecture on Monday?
No, and there's no lecture on Monday. Yes, thank you. Thank you for reminding me.
Are we having lab, or are we not having lab the last week in December?
We won't have. That's a good question.
Since the last deadline for Lab 5.
Yeah, I think. Let me see. Let's check the syllabus here and get the dates straight. Okay, so we have the final exam on the 6th. The project cutoff is on the 3rd. Last lab is on, oh, I'm sorry. Yes, that's a good point. So we actually have, there is a lab during the last week. So yeah, so actually that last lab should be, I guess I was off by 1 week there. So yeah, project cutoff, it would be the 3rd. Yeah, so it should be the 3rd. I'm sorry. I had that wrong. So I'll update that due date.
Can we have extension for Lab 5 to have project cutoff on December 6th? Because if deadline for Lab 4 is 28th, then you have 2 + 3, 5 days to finish Lab 5.
Sure.
So maybe we can have extension until December 6th for Lab 5.
That should be fine because our final exam is, yeah, not till the 6th. So yeah, that should be fine.
Yeah, thanks.
Yeah, so that lab cutoff that won't apply for the graduate, yeah, the graduate lab. Okay, yeah, so sorry, let me update that now. So that will be 12/3. Yes, that should be 12/3, and yeah, and then we'll have that last week. Good, well that'll work out nice. Because then, that'll give me, if you need any help finishing it up, we'll be there for you. Okay. So as I mentioned, we've got Lab 4 is posted on Moodle. And I asked Charles to try to cut down the length of this lab sheet a little bit. They were getting pretty long. This one's still 9 pages, but the second half is just he still has the list of all the instructions there just for reference. But as I mentioned in class, the objective is to implement the branch and jump instructions, which are, need to reopen that file. Okay. Okay, so we've got branch of equal, branch of not equal, branch of less than, branch of greater than or equal, branch of less than or unsigned, branch of greater than or equal unsigned, jump and link, and jump and link register. And then we want you to deploy the square root program on the board, which you guys have already written the program and you've already got the bin to deck. So you're going to reuse the square root code as well as the bin to deck code for this lab. And so you're just adding, 8 instructions to your CPU. However, most of these, the branches are all very similar. So they're kind of like the distinction between the different R-type instructions. They basically just require everything, all the control signals are the same, the only difference is the way the branches are resolved. Okay? So, specifically, how do you update lab 3 to lab 4? Okay, well, as you guys know, lab 3, that was a lot of work. Lab 4 shouldn't be as bad because there's really just 6 things that you need to do. You need to calculate these branch, jump and link addresses. So I mentioned in class last time that the way that you calculate the target of the branches and jumps depends on which instruction format you've got. So we have 3 different instruction formats. You might say, wait a second, I thought there was just 2 new formats, B type and J type. Yes, but the JALR, I believe, is actually an R type, right? It goes back and uses I think this one's R type. Okay, so there's 3 different ways to calculate where you want to branch or jump to, and I gave you the code for that because it was ridiculously confusing. So the code for those are actually in the slides. Then you want to add a PC mux. This is new because previously the program counter would always just get PC plus 1. It was literally just a counter, whereas now you have to add a mux that will allow you to select among 4 different options, either PC plus 1 or one of these 3 targets. So how do you implement that? That's a ternary continuous assign statement. So that's, in other words, it's combinational logic. It's just a mux. And that will be controlled by a control signal called PC source EX, which will be a new output from your control unit. Now you might say, wait a second, do I have to add that every single place in the control unit that drives output signals? No, because you can set a default value for that PC source EX to 0 at the beginning of your control unit, and then you just set it to anything other than 0 wherever it needs to be set. So you can, it's not too bad. Then you need to add a stall fetch as an output of your control unit, and again, you can just assign that to 0 by default. And you need a stall underscore EX as an input. So this is a thing I was talking about where it's like a feedback. You have a stall fetch comes out, goes to a register, and then it comes back in as a delayed version of itself. Make sure that register is there or you can end up with a combinatorial loop, right? You want to make sure that this signal has a register that breaks up the timing, that delays it by 1 cycle. And basically that's just used whenever you take a branch or execute a jump, you issue the stall signal, and that just means that the instruction that is being fetched while the branch or jump is being executed is just ignored. And then you have to add the decoding maps. I call them decoding maps, but if you guys have a decoder that basically takes the instruction format and breaks it into, like renames the different fields, you can add that for the J and B type instruction, which should be pretty straightforward. It's just renaming things. Then you want to add the PC fetch as an input into the reg select mux. So what I mean by that is you had this reg select mux that controls what gets written back into the register file. And luckily, we have a spare input on that, right? Because there was 3 inputs. So if we add a 4th input, we don't have to increase the size of the select, right? Yes?
PC fetch is for jump and link here.
Yes, this is for jump and link. Yeah, so this gives you the ability to write the PC fetch to the reg file. But I just realized something just right now, actually. PC fetch, should it be PC fetch?
PC write back.
Well,
PC fetch plus 1.
it should be PC write back. That's a good point. So here's the problem with that. Remember that PC fetch is the instruction being fetched, PCEX is the instruction being executed, and PC write back, right, would be the PC of the instruction being written back. Okay. Now, when you do a jump and link, your goal is to write the program counter value for the return address, right? So if you were to if you wrote PC write back here, then the value of that when the jump and link is being written back would be the address of the jump and link, right? So if you wrote this one and you returned, right, from the subroutine, it would go back to the jump and link again, right? What you really want is you don't want PC write back and you don't want PC fetch, which is what I had there before. You actually want PCEX because PCEX refers to the instruction that's behind the jump and link, right? So what that means is when the jump and link is being executed, you actually want PC fetch. But when you write back, by the time you write back, the jump and link is now in the write back stage, and the instruction behind it will be in the execute stage, right? So you really want PCEX. Make sense? So you want to be careful there, because if you don't have this correct, everything will work fine until you go to return from your subroutine, right? And you will return to the wrong spot. You want to return to PCEX because when, another way to look at this is, if you had a register here, then you would have PC fetch coming into that register and PCEX coming out, right? But I'm not showing the register. I'm just, although it would probably be more clear if I did. But I'm just going to call it PCEX, which means the address of the instruction that's now in the EX stage when the jump and link is in the write back stage, right? It's the next instruction in the program. Okay, so sorry about that. Okay, so I think, I think that's, wait, where's my list? That's another list. Yeah, add PC fetch. Yeah, and again, that should be PCEX. PCEX, and then add entries to the control unit. Now, the other thing that's tricky here is the branch resolution logic, right? So the idea is that inside your control unit, you're going to say, if it's a branch, then I have to set up the ALU to do the branch resolution, meaning that, if it's a branch of equal, I'm going to tell the ALU to subtract, right? Then, if you're going to have a nested if statement, you don't have to do it this way. I think this is the easiest way. To me, this is the most straightforward way to do it. You'll say if it's a branch, meaning, if the opcode is whatever the branch opcode is, right? Branch of equal opcode. Then you'll say, okay, set up the ALU, and then inside there you have a nested if statement that says, if the result of the subtract is 0, then set the PC source in the stall accordingly, right? See, remember, the outcome of the branch is really just the PC source and the stall, right? Anytime the PC source is anything but 0, your stall is 1.
What again is PC source?
That tells where to go next. Like if PC source is 0, it means just go to the next instruction. If PC source is anything other than 0, it means you're going somewhere. You're changing control. You're either going to a branch target or a jump target. Yes?
Can we use output from like in our lab 3 we have output 0, which we not quite use in lab 3. Can we use it in lab 4? Like we had subtract. If subtract is 0, it means that they're equal, so use output of 0.
Sure, yeah, there's a 0 flag. Yeah, that's what that was for. Yeah. Yeah, that 0 flag is, I think last semester, we used to have it in ALU, and then we took it out. I can never remember if it's in there or not. But if it's in there, I would use it, yeah. Yep. Okay. Okay, so let's move on to the next topic then, which is sequential logic design. Okay, so we've talked a little bit about this already, but we haven't given it a formal treatment. So we talked about there's combinational logic and sequential logic. Combinational is when you have outputs that's a function of inputs. Sequential is when you have your output as a function of not only the input, but some input history or some memory, right? So sequential logic is, to try to define these terms, logic whose output depends on the inputs and the sequence of past inputs, right? But that's very vague. It's like, okay, but it's just the sequence of the previous inputs. However, if you say synchronous sequential logic, that's a little bit more specific, where the synchronous part of this implies that it's not only sequential logic, meaning that it's using the history of the inputs as well as to determine the output, but also it specifically says there's a clock. It's synchronous to a clock. So if you say synchronous sequential logic, that implies that you're using an edge-triggered flip-flop to create the history, the memory, right? So this is a little bit more of a little bit synchronous sequential logic, a little bit more specific. There is asynchronous sequential logic, and that's when you don't have a clock. And you can build asynchronous sequential logic circuits. The way that works is that you don't have a clock, so the way that you control it is you make sure that the state is only changes when any of the inputs change. So basically, you use the inputs as the clock, right? And you can do that. In fact, when I was in school, we had a unit on that, and we had to actually build them on breadboards. The problem is that no one really uses asynchronous sequential logic because it's very hard to design to make it stable. And the reason is because logic has glitches sometimes when you design complex combinational logic, and a glitch will really screw up asynchronous logic. So when you design asynchronous logic, it has to be timed very precisely, which often makes it impractical, right? Especially if you're doing any kind of arithmetic circuits like you would have in a CPU. So while it would be nice to have asynchronous sequential logic, you might say, well, why would it be nice? Well, because the clock is, when you have a clock that's connected to everything on the chip, that uses power, right? You have this clock that's constantly running. It's inefficient. It would be much more power efficient, energy efficient, if we could build things with asynchronous sequential logic. It's just not practical. Okay. And then state, whenever I say state, I'm talking about the information, the historical information required to explain the future behavior of a circuit. So in other words, what I mean by that is when you say that the output depends on the input and the sequence of past inputs, the state is the memory that you use to record the past inputs, and depending on how much state you have determines how far back into the past you can look, essentially, right? That you can record, right? That's what state. And then, as I mentioned, state itself is typically going to be latches or flip-flops, normally flip-flops, right? Okay, so how do you make, we already talked about this, but just to quickly review. In System Verilog, there's two ways that you can create memory. When I say memory can be a RAM, it can be a latch, or it can be a flip-flop. We can do typically, like you guys should be used to by now, saying always _ FF at pos edge clock. Basically anything in there is clocked, right? It's basically a flip-flop. It's an edge active memory. This is the style you should always use for your memory. However, you could create a latch. Some of you guys may have gotten an error. You might have accidentally created a latch. So for example, if you have something like this where you say always comb if A equals 1, then B gets C, but then no.
If A equals 0, what?
Yeah, like if A is 0, then what does B get then? Unclear, right? Like if there's not an assignment for all the outputs through all the control paths of the always statement, then this will create a latch. So basically what happened is that B will retain its old value if A is 0. So that A becomes a latch clock, essentially. Now, hopefully this won't actually do that, because notice I said always comb. So System Verilog has this always comb. It's supposed to protect you, because if you write this line of code, you should get an error saying, you said it was combinational and that's a latch behavior. But sometimes I think ModelSim actually doesn't do that. I think Quartus does that, so you have to be careful. Now there is an always _ latch if you really want to create a latch, or if you say always at, if you just use the always at star, like, actually I should have said always at star. There's an always at star syntax, right? Which is a more of a generic always. If you don't put comb, you don't put latch, you don't put FF. Always at star, this is the way that this was the only way to do an always in regular Verilog before System Verilog came around. Then you can end up with a latch. Now you might say, well, okay, so how does a latch work exactly? Okay, so a latch, so let's say we have a clock and we've got D, right? D is our input. Say we have two outputs here, two lines of code. One is a latch and one's a flop, should say flip-flop. Okay, so the latch would say always at star. If clock equals 1, then Q gets D. This is the latch. Whereas a flip-flop would say always at pause edge clock. If clock equals 1, then Q equals D. Right? So they're pretty similar, right? The only difference here is this pause edge clock. But the difference is that with a latch, basically what that means is it's level sensitive, meaning that whenever the clock is high, the output of the latch will basically be whatever D is, right? So while clock is high, if I raise D, then Q goes up, right? Now the problem is that if clock goes down, then whenever clock is down, whenever clock is low, it locks in the value of Q, right? Which actually doesn't happen yet, because by the time D changes, clock is back up high again, right? So, D comes down, Q comes down, right? All right, so no problem. Then D goes up, Q goes up, right? So pretty much D and Q are the same thing as long as the clock is high. But once the clock goes down, which it does here, it's gonna close the gate down, right? So now when D goes down, Q ignores it, right? On the other hand, if you have a flip-flop, then basically Q never changes except on the rising edge of the clock, in which case it takes a picture of whatever D was at that moment in time, right? So clock goes high, and it's going to sample Q. So sample D, is sample D. So D is low, so D goes low, right? Now you might say, wait a second, why is Q high and low here? Well, it's because I don't know what it is yet. I won't know what Q is until the first rising edge of D, right? So the reason why it's both high and low is because, The reason why Q is high and low here is because I don't know what it is right now. But when I get the first rising edge of the clock, first rising edge of clock, and then this will respond, right? And then the next rising clock edge is here, and that's why it's gonna capture a high D, which will drive Q high. You guys with me? So, you guys, I think you already knew this, but I just wanted to make sure everyone was clear on this difference. Now, can you do a latch on an FPGA? I actually don't know. I don't think I don't know. I've always been afraid to try that. It might work, but the tools will not be happy with you, and it may not compile. Okay, so then a register, again, a register is just, flip-flops, right? Parallel flip-flops, so, 4 bits for D, 4 bits for Q, right? You guys are with me on that. So you guys are familiar with that, and of course we talked about that you can have an enable, you can have a reset. The only enable you guys actually have in your design now is the GPIO out, right? So when you have the CSSRW instruction, you're supposed to update the hex display, so you need to enable a register that controls that. That's the only enabled register you guys have. Well, aside from the register file, which has a write enable too. But that's not a register, that's a RAM. And then of course resettable flip-flops, I don't think we even have any of those. Oh, a program counter. Yeah, program counter is a reset, right? When you reset, you want the program counter to go to 0. That'll basically boot your computer, right? Hit the reset button. You go to 0, address 0. That's your bootloader, right? You start fetching your bootloader. Okay. Okay. So you could also do things like, instead of just having just a flip-flop or a register, you could do things like this. You can put some logic in there, right? So for example, this is a counter. So you can say always _FF pause edge clock. If it reset the counter. I should have put, how many bits is this? 6-bit counter? It should say 6 apostrophe. I got that. See, that wasn't my fault. This is from the book slides. This is the textbook author's left. Technically, it should say 6 apostrophe B0. It still works, yeah. I think what it does, though, is that the compiler assumes that 0 is 32 bits. And then but it's better if you specify it. Okay, so anyway, if you reset the counter to 0. If reset is 0 on the pause edge of the clock and you enable up, right, is 1, then it'll increment the counter. Otherwise, if enable down, it'll decrement. So kind of like your program counter, sort of, except this thing has the ability to go up and down. And by the way, your program counter in your CPU can work the same way, except you could say, if PC source is 0, then increment PC fetch. Else, if PC source is 0, 1, then use the branch address, right? So you could design your branch logic in this same style, right?
So for branches, we feed the value from the register file, right? For the PCX.
No. The branch target is the PC relative address. So you're going to do that calculation that I gave you, where you take PC fetch, which is the current PC, and you add the offset from the instruction.
Yeah, but you store it in the right file, right?
If it's a jump and link, yeah. Yeah, if you link it, yeah. Yep. Okay. So basically, we've talked a little bit about the that stuff was all sequential logic when you have the memory, right? But there's other types of sequential logic. There's this thing called finite state machines, and there's also pipelines. Well, we've already built a pipeline. You guys are already familiar with that, right? Finite state machines is another type of circuit you may need to build. A finite state machine is used for things like when you have a bus, any kind of a bus handshake that has to happen, where you have this sort of two entities that you have to go through different stages of sort of agreement, right? Or you go through different phases of a protocol. Another example is if you have say a multi-cycle CPU. Like right now you guys have a pipeline CPU, but you could design a CPU that instead of executing fetch, execute, and write back at the same time, you could do them in 3 cycles. So you could create a multi-cycle CPU where there's only one instruction being executed at any time, but it goes through 3 phases, right? So you fetch it, you execute it, you write back, and then you go back to fetch and you get the next instruction, right? Now obviously that would be slower because it would take like 3 cycles to execute an instruction, and your CPU right now can do it in 1 cycle once the pipeline is full, right? So, yeah, those are FSMs, or nowadays are mostly used for handshaking protocols. So an FSM is kind of like you might say, what do you mean, a finite state machine? Where's that term come from? It's like the theoretical model of a machine that runs with sequential logic, right? So you could actually model a counter, or your program counter is actually a finite state machine. We just don't think of it that way. A finite state machine is defined by its inputs, its outputs, and the set of states that it can go through. Now, in the case of your program counter, what are its states? It's pretty much its count, right? The program counter state, which is from 0 to 4095, and then back to 0, right? Yes.
So the set of states is at our memory, right?
It's the potential configurations of the memory, right? Which isn't necessarily every possible bit permutation that can go in the memory, but it's every possible content of a memory, depending on how you have it designed. So it's not necessarily 2 to the power of the number of bits, it's the number of possible values, right? Now you could design the circuit so you can't go through every possible value, right?
Yeah, but that's the maximum number of our states we can.
Right, yep.
Yeah, thanks.
So there's 2 ways that you could design a state machine. You have this thing called a Moore machine. So basically what a state machine does is, you could think of it like, it's like having a lookup table, like a truth table, right? But the truth table can change in every cycle, right? Now the problem is, if you just think of it that way, if you think of it like that, then that implies that the outputs are asynchronous, in the sense that if I change an input, then the truth table will give me an output. The output I get might be different depending on which state I'm in or what cycle I'm in, right? But every time I change an input, the output will immediately update, right? That would be called a Mealy machine. There's another style called a Moore machine that's a little simple that basically says that the outputs are only a function of the state that you're in, meaning that you only will see a change in your outputs when the state changes, basically once per cycle. You guys with me? Now, it turns out the distinction is actually it's probably a minor distinction. But I'll talk more about that here as we go and show you an example. So let's look at a real simple example. This is a traffic light controller. So the idea here is that we want to control a traffic light at an intersection between two roads, and we have a sensor. So it's not controlled by just fixed time intervals, right? It's controlled by when cars actually approach the intersection. So we want to be able to change the light whenever we have basically traffic at the red light. We want to make it green, right? So our inputs will be, we have two roads, A and B. They stand for Academic Boulevard and Bravado. Is it street? Boulevard, sorry. Academic Avenue and Bravado Boulevard. This is the names that they came up in this with this.
The Assembly and Blossom, probably.
What was that?
That should be probably Assembly and Blossom Street.
Yeah, that would probably, yeah, you're right. I should have renamed them. So the TA and TB is traffic detector at Academic and Bravado, and then LA and LB is the light, which light you're showing on either one. Now LA and LB are actually 2-bit signals because you have to choose between 3 options. There's red, yellow, and green, right? So each of these are 2-bit signals. So in total you have 4 bits out and 2 bits in, and of course there's the clock and the reset, right? So it's basically, it looks like this. You've got the traffic detectors. Now the TA and TB, the way it's shown on here is traffic is detected on Academic, can be detected on either side, right? Just like there's 2 detectors on both sides of the intersection on Bravado, right? And so basically those are just going to be true or false depending on whether there's a car sitting at the intersection or not, right? On either of those streets, okay? And so when you create this thing, you have to think about, well, how many configurations is it in? Well, obviously you can only have a green light on one street at one time, right? So you're either going to have green on Academic and red on Bravado or vice versa. There's 2 states, but you have to also consider the yellow light configuration as well. So you have to give some time for a transition from green to red, which is the yellow light. So that gives you 2 more states. So there's actually 4 states, right? Basically green light at Academic, yellow light at Academic, green light on Bravado, yellow light at Bravado, right? And then in each of those, there's the red light on the other street, right? So there's 4 states. And so whenever you have an FSM, you have to decide on which state is the start state. That's where you go when you hit the reset button. We used to call it the sanity state. And that's marked by this little arrow coming from nowhere, right? Okay, and then, so in a Moore machine, I mentioned there's Mealy machines and Moore machines. In a Moore machine, you'll draw the state as a circle, and the outputs are inside that circle, because the idea here is that every state has a fixed output, right? So once I'm in a state, I have my outputs are set just depending on that state, right? So it doesn't matter in this case, like once I'm in a state, I'm going to have the traffic lights will be driven to a certain configuration, and I'm not going to change that till I change states. I can only change states on a clock edge, and no matter what the traffic detectors do, it's not going to affect the outputs at all, right? And so that's why this is a Moore machine. And so the states are circles, and then you have transitions that determine which ways you can go from one state to the next. So obviously one way to think of this is, well, if I have a state, I should be able to go from any state to any state, right? But in fact, when you design one of these, you want to limit the possible transition. So if you're in a state, you only want there to be certain other states you can go to, right? And those are defined by these, basically lines with arrows, right, that show you how all the possible transitions, right? Now, in a lot of cases, you'll have a loop-back transition, meaning that if you're in a state, there can be a combination of inputs that'll cause you just to stay in that state, right? But then you'll have other states like this one where there's no loop-back transition, which means that at most I'm only going to be in here for one cycle at most, and then I'm out. It's just a temporary. Like once I go to this state, I'm only going to be there for one cycle. And that's how this yellow light is going to be implemented. That's how we're going to be able to establish a time in which the yellow light will be lit. In this case, the yellow light's going to be on for only one cycle, and obviously the cycle time is, going to be, 10 seconds or something like that, right?
It's like stable state and unstable state.
Yeah, well, they're all stable, but it's the difference is whether or not there's any way to stay for more than one cycle in a state, really. That's what this is. So whenever I have a yellow light on academic or bravado, so there's a yellow light here on academic, there's a yellow light here on bravado. I'm only going to be there for one one cycle, and I'm going to set my cycle period to about 10 seconds or so, right? But on the other hand, if I've got a green light on academic and a red light on bravado, I'm going to stay in there indefinitely as long as I've got traffic on academic. Right, as long as I still have cars on academic, I'm going to stay in there. However, if the traffic on academic dies down, and I got, if it dies down, then I'm gonna get out of that state, right? I don't even, not even gonna wait for traffic on bravado. I'm just gonna say if there's no more traffic on academic, I am going to change my light to yellow, stay there for one cycle, and then I'm gonna switch the light to green on bravado. And I'll be there as long as I've got traffic on bravado, right? Now you might say, wait a minute, why don't you wait, why isn't this TB here? It says not TA. You could design it that way too. That's just the way they did it. Instead of waiting there for it to be traffic on bravado, they just said once the traffic is gone on academic, then I'm going to move out of its green light state. Right? Does that make sense? So not TA. Yes.
Theoretically, if there was traffic, like consistent traffic on both, would there be like a time limit?
There should be, yeah. That's not built in, so you'd want to put that as like a another input, like a timer, like a watchdog timer, or you could have, instead of being in one state, you could have a sequence of states, that implements that timer. You know what I mean? Like you could say, well, I'm not going to stay in this state. I'm actually going to make this a sequence of states, right? At which point I could bail out early. Yeah, there's different ways you can do it, but in this case, yeah, technically it's possible for, there to be if you keep getting traffic on academic, then the light will never change for bravado, right? Yes.
If it's in the middle of the night and there is not TA and not TB, you got this light show when.
Yeah, it'll continually switch, right? It'll go green, yellow, yeah, that's right. Yeah, this is obviously simplified, just meant to be a simple example. Okay, so generally the way that you go about implementing this is you create a state transition table, which is a truth table, and the idea is, yes?
Can you please change the color of the...
Oh yeah, sorry. Yeah, that's a good point. Layout, shading. Yeah, that's a good. There we go. It's a little better. Okay. So you want to create this. Basically, the first thing you want to do is you want to implement the transitions. These transitions. Each one of these transitions can be built with a next state table, right? So we're going to ignore the outputs for now. We just care about the transitions. Now, in order to do that, notice I've named. Well, actually, the book named these S0, S1, S2, and S3. So you can give symbolic names to these. And in fact, in Verilog, or in system Verilog anyway. Actually, in Verilog too, you can create symbolic names in Verilog, but the way you do it is a little different. But the point is every state usually has a name, right? However, when you go to build it in hardware, you will eventually have to assign values to those states. But for now, we're just going to leave them symbolic. So we have a table where we have a column for the current state and the column for the inputs, and then a column for the next state. So the way that you build this in hardware is that the next state is your D input. Like if you have a register, you have a D and a Q. The D is going to be the input to the register. That's your next state. And Q is the current state. Okay? So then the logic that you get from having built this table is the logic that's going to go between Q and D. So you have basically the way you build this is you have a Q comes out of a register, it goes into a blob of logic, which is the combination of logic you get from this table, and then the output of that logic just feeds back into D, right? So again, this is Q and this is D essentially. Now the tricky part is that these tables get big really fast because the number of rows in this table is potentially 2 to the power of the number of bits that comprise both the state and all the inputs, right? So these tables get big fast, right? However, normally you have a lot of don't cares. There's usually a lot of redundancy in here, right? So you'll notice that in this table, I've got some X's that represent don't cares, which you can exploit. When you guys probably, hopefully you learned about don't cares in 211 with regards to, logic minimization. But in this case, if I'm in state 0 and I have no traffic on, now remember S0 is green light on academic, right? So if I have a green light on academic and no traffic on academic, then I'm going to go to that yellow state, right, on academic, which turns out it was S1, right? On the other hand, if I have traffic on academic, then I want to stay in S0, right? So this is S1 and that's S0, right? So basically all you're doing is every one of the rows of this table corresponds to one of the arrows. Every one of these arrows gets its own row in the table, right? So you can literally just grab every one of these little arrows and just match it up to one row on the table. Okay, so now again, this is, let me change the color here again. Table design, shading. There we go. Okay, so yeah, if I'm in, let's say S1, which is my yellow light, well, remember, this is the one I just pretty much stay in for one cycle. So in this case, both of the inputs are don't cares because, after one cycle, I'm going to immediately transition from S1 to S2. S2 is the green light for Bravado Boulevard, right? So that's why these are both don't cares, right? And I only need one transition in here because you might say, there's only one transition here, right? But over here, I had two transitions, right? I had the loop back transition and I had the outgoing transition. So if you look at S2, I should have 2 rows of the table for that, right? That's why I have these 2 rows here, right? So that's the next state table. And then you have to assign values to these symbolic names. So again, let me change that to black so it's easier to read that. Black. There we go. Okay. So I know it's a little small. I wanted to fit this on one slide. So I'm going to arbitrarily assign values. Now, how many bits do I need? Well, I mean, there's 4 states, so I need at least 2 bits. But you could choose to actually have more bits because it turns out that sometimes by having more state bits, you can simplify the logic, the next state logic. But in this case, I just have 2 bits. And so I've replaced each of the states with S, instead of S0, it's now 0, 0, right? And then, of course, instead of S1, it's going to be 0, 1. So I filled in this with 0, 1, right? Okay, and then now for the output, that's just the next state. For the output, change this again. There we go. Okay. So for the output, I have to also associate binary values that represent each of the 3 possible outputs. Obviously, one of those I'm not going to use. There's 4 possible encodings. So green is 0, 0, yellow is 0, 1, red is 1, 0. Now remember, though, that there's light A and light B, so I have to set them both. So there's actually 4 bits. And notice that each state, because it's a Moore machine, because the output is the same, is consistent, is constant. The outputs are constant in each state. I only need 1 row of this table for each state. If this were a Mealy machine where I allow the inputs to affect the outputs as well, then I would need additional columns in here for my inputs, right? But it's a Moore machine, so just 4 rows for 4 states, right? Does that make sense? Okay, so now normally, if this were a like a regular digital design class, we would be building these things, and I would be asking you to design, Boolean logic to implement these, which is, what they should be covering in 211. I don't think they get to this, though. But this is the Boolean logic to actually implement this, right? But because we're using System Verilog, we don't have to worry about that. We can take advantage of System Verilog to build these guys. But the process is pretty simple. So the first thing you want to do is you want to create, you don't have to do this, but this is a common style for actually translating an FSM into System Verilog. The first thing you want to do is you want to create an enumerated type in Verilog. So you say type def enum logic 1 down to 0, S0, S1, S2, S3, and that's called state type. I never remember this syntax, ever. I always have to go back and look this up because I can never remember, because there's so much going on here. There's type def enum, but then you have to put logic 1 down to 0, which is telling the compiler that, yeah, it's an enumerated type, but it's 2 bits. I don't care how you assign those 2 bits to each one of these, but it's a 2-bit thing. And then you give it the names, and then you put the state type, and then you use state type as opposed to logic to declare the current state and the next state. So you need to have internal variables for each of those. Yes?
So in this declaration, you say that we have some state type which is 4 states, each of one consisting of 2 bits. So in total 8-bit bus.
Right. Well, no, actually, no, it's not 8. There's 2 2-bit signals. So there's each one of these is a 2-bit signal. What you're telling the compiler is you want the compiler to decide how it's going to represent each of these 4 values as a 2-bit encoding, which is what I showed in that table. No, not that one. Sorry. This one. This table, right? So notice that I did it manually here, where I assigned S1 is actually just a alias for 0, 1, or it's like a parameter, or a definition, or a symbol, macro, that's the word. It's like a macro, right? So you just allow the compiler to do it. You might say, well, who cares? I mean, why not just do it yourself? You can just use bits instead of state names here. But by doing this, you give the compiler the flexibility to minimize the logic by choosing state encodings that minimize the hardware. Yes?
State type is 2-bit. It's 2-bit value. value, right?
It's a 2-bit value, but when you assign something, you can assign values like S0 to it, as opposed to an actual 2-bit value.
But what if you say that it's 2-bit but give five literals?
Oh, I don't know. It'd probably give you an error. That's a good question. I never tried that. I don't know. I'm assuming it could give you an error. Okay, so then.
I'm sorry, but potentially you can put three literals.
Oh, sure, yeah. Or you could literally just say, 7 down to 0 here. You can make it 8 bits and only have 4 values. That's fine. That gives it more power to, decide how to encode them.
Thank you.
Okay, so the. By the way, I don't know how much difference that makes. By the way, the real challenge with FPGAs is placing and routing. The synthesis part that figures out the truth tables and the Boolean logic, the CAD tools don't spend as much effort on that. So I don't know how much difference it makes, to be honest. But by having these symbolic names, it makes it easier to read the code too. Okay, so then you need to have your state, your memory, right? So generally you'll have one always block that just takes care of the memory, right? And it's very simple. All you have to say is, if reset, it's always a pos edge clock, pos edge reset. So if you have a reset, then current state is going to be S0, because that was your sanity state, right? That was your reset state indicated by that little squiggly arrow. Otherwise, you're going to take your next state and put in your current state. So really, this is just the same logic as a D flip-flop. The only difference is instead of D, it's called next state, and instead of Q, it's called current state, right? That's the only difference. But you have to, that's the stuff that actually takes care of the memory. Then you can have a separate. You can have a separate. Always block that implements the next state logic. The next state logic is combinational. It just takes the current state as an input, and it outputs the next state. But it doesn't have any memory. It's just combinational logic. So you can say always comb, right? Now this is what I'm showing here on the left is actually the next state logic if it were lowered down into logic gates. And you could do this. You could build a little truth table and actually manually by hand create this, because it's a small circuit. Obviously, if you have more bits involved, it doesn't become practical. But this is what the compiler, the synthesizer, is going to generate. But this is all you need in System Verilog. You can just say always comb. Now this is a little weird. Check this out. I did a little trick here. You see the first line of code says next state equals current state. That's the default, right? That's what you guys should have in your control unit on your CPU. You should always start these things out with a default. So that way, if I get through this if statement and I never assign the next state, I won't create a latch because I've got this default. And basically what this default says is that if none of these conditions in here match, just assume I'm staying. I'm staying in the state I was, right? So basically what this has done is this adds a default loop back transition to all my states. So then I say, okay, if the current state is S0 and the traffic at academic is 1, then next state is S1. Otherwise, if the current state is S1, that's when my yellow light is on academic, and that's the one I only stay in for 1 cycle. I don't care about my inputs, and because the inputs are don't cares, I don't include them in this if statement. I just say, hey, if I'm in S1, next state's S2. That'll give me that 1 state visitation in that yellow light state, S1. And then if I'm in S2, that means I've got a green line on Bravado. If I've got traffic on Bravado, I think I screwed that up. Sorry. Hold on. If I'm in, this should be Bravado. And this should be academic. Sorry. Because if I'm in, sorry, I had that switched. Sorry. So just to explain that, if I'm in S0, I've got a green light on academic. I'm waiting for there to be. Oh, actually, no. Sorry, I got that wrong again. The way that it was written was if there's no traffic on academic. Remember, it said not not TA?
Yeah,
sorry. So I had it. Sorry.
It
was not TA was the condition for transitioning there, right? Yeah, so basically if I go back up here, right? So yeah, the condition was TA is 0. If I'm in S0, wait a minute, that's harder to read. Hold on, let me go up. Go back to the symbolic version. Yeah. So if I'm in, wait a minute, back up again, sorry. Yeah. If I'm in S0 and I have no traffic on academic, then I'm going to go to S1, right? Likewise, if I'm in S2 and I have no traffic on Bravado, then I'm going to go to S3. So the code should say that, right? Yeah. So if I'm in S0 and I have no traffic on academic, then I'm going to go to S1. And if I'm in S2 and I have no traffic on Bravado, then I'm going to go to S3. And if I'm in S1 or S3, I stay there for one cycle, meaning that I don't care about any of the inputs, right? And notice here, I don't mention TB. So TB is a don't care. Here, likewise, TA is a don't care here, right? So this block of logic then is my next state logic. And then for my output logic, I can create another block of logic that takes care of the outputs. And the output logic is, again, combinational. And I'm going to have two default statements. I'm going to set them both to green. Obviously, you might say, well, wait a minute, that's kind of dangerous, right? Well, yeah, but if you go through this code, I might set them both to green by default, but I'm going to change one of them to red before I get through this code, right?
So why don't you put them both to red?
I could have done that too, yeah.
It's kind of safe here.
Yeah, it would have been safer, yeah. But I set them both to green because then if I'm in S0, I'm going to set Bravado to red. And if I'm in S1, I'm going to change them both. I'm going to have academic as yellow and Bravado as red. If I'm in S2, I'm going to just change academic to red. The green Bravado will be green from the default. And then if I'm in S3, then academic is red and Bravado is yellow. I could have set them default to red and then just change which one was supposed to be green. But yeah, so that's the output logic. And again, it's combinational. And it turns out that the actual Boolean logic here is almost trivial because you're just taking a 2-bit state and you're translating it to a 2-bit output, for these guys. And so, the actual logic gates here is very simple. Now, as you might imagine, though, you could make the state machine much bigger in System Verilog very easily, whereas if you had to do it this way, it would become impractical pretty fast. Okay, so here's the timing diagram. Now this looks a little crazy, but the idea is that, first of all, when you're doing these timing diagrams, you always got your clock, right, is just, just oscillating. And you notice these, these dotted lines are marking the rising edge of every other cycle, and there's like a faded dotted line there for the cycles in between, right? And so what's happening here is that we start out we have the reset pulse there, which puts us in state S0. Now S prime is the next state actually, and S is the current state. So we should be looking at S to figure out what our current state is. So our current state is in S0, and pretty much we're going to stay there until our academic traffic goes away. And that happens right here, that drops, right? Now we're not going to switch states right away because I can't switch states until the clock edge. So I'm going to look for the first clock edge that happens when the academic traffic indicator goes to 0, right? At which point I'm going to go to state S1, which is our yellow light. So when does that happen? Well, it looks like I missed that one. It was too late for that clock edge. Look at that. The traffic sensor dropped right after that rising edge. I just barely missed it. So now I got to wait till the next rising edge. So I got to go all the way over here to cycle 5, at which point my state does change to S1. Now you might say, well, what about this guy? Well, this was the next state logic. So remember, the next state logic is asynchronous. Anytime the inputs change, the next state logic will update right away. But the current state is only going to change on the edges, the rising clock edge. So even though the next state changed to S1 back here, I didn't actually go to that next state until cycle 5, right? So at that point, that's when the yellow light comes on academic, and then, of course, I'm only in there for one cycle. I'm going to go to S2, where academic is red and bravado is green, right? And I'm going to stay in that until my bravado traffic indicator goes to 0. So when does that happen? Right there? Again, I just barely missed that clock edge. I got to wait till the next one, at which point I switch to S3 and I got a yellow light at bravado, right? So yeah, basically you know, the way I read these is I look for those, pretty much you just look at what happens on the rising edge, right? Now it's, the whole idea of synchronizing everything on the rising edge of the clock is going to become clear in the next lecture when I talk about timing analysis, because the problem is you can't, if you look at this next state logic, because it's combinational logic and logic has different paths that go through that logic, different length, different delay paths, you might find that there's glitches on this next state logic. They don't show any glitches here. But the next state logic is, it's a little glitchy whenever you change an input. It takes it time to stabilize. And so by only looking at the next state on the clock edge, it gives the logic time to stabilize. And we're going to be talking about that in the next lecture when we talk about timing analysis. Now, we don't have a lecture next Monday because I'll be at St. Louis at this conference. I'm running a workshop. But I'll be back. I'll see you guys in 2 weeks, okay? And we'll talk about timing analysis.
Next week, no lectures, no lab.
Yeah, no lecture, no lab. But I'm flying in on Sunday, and I'm going to be flying out on. I'm going to get out early. I'm going to try at least, assuming I don't get canceled, on Tuesday, right? So I'll be here starting Wednesday next week. So if you need help.
So we can ask you on Wednesday if you can help us.
Yes. Yeah.
Okay.
Exactly. Okay. Thank you.